there's just a number of challenges. Firstly, the whole question about making chemistry much more energy efficient. We had the luxury the first time round, energy was cheap, it didn't really cost very much, but that's going to change. And there's some really important processes where chemistry is necessary, I believe, but we do need to get the energy down. One of these is the whole business of fixing nitrogen. If we don't have fixed nitrogen to feed to our plants, we don't get any protein, we don't get any DNA, because that's pretty much where all of our nitrogen comes from, through plants. But it is enormously energy demanding. Now, in theory, some of this can be done biologically. There's fixed nitrogen in the soil from lightning strikes and the nitrogen in the air, and plants themselves fix some of it. The problem with the biological area, which is a grand challenge, and the biologists are really working to try and make all plants fix their own nitrogen, is energy. So it takes a lot of photosynthetic energy to fix nitrogen. And so the yields are predicted to go down by perhaps as much as 40% if you took a crop like wheat and made it fix its own nitrogen. So although the chemical fixation of nitrogen is very energy demanding, so is the biological one. And my view is that chemistry, really modern chemistry, ought to be able to do at least as well as biology. So there's some great challenges, really efficient fixation of nitrogen, a whole load of other things like this, so just really trying to improve the energy efficiency. The last but one area is the whole business of trying to defeat entropy. We tended to use some pretty low abundant materials. Traditionally, for example, phosphate as a fertilizer, we've almost exhausted the really rich sources of phosphate minerals. But of course, more recently, there are things like rare earths, which aren't called rare earths for no reason, but we tend to use them and then just put them back at the mercy of entropy, back into the environment in a dilute form. And I think that that's really not sustainable. When we have some of those critical ingredients, we need to do much better at recycling them. And it's kind of linked in with water purification. There's plenty of water in the world, but a lot of it's got salt in and low levels of things that we don't want. So it's no good for drinking and no good for growing food. And I think the whole energy efficiency of extraction to both collect the things you want and to leave yourself with water that's palatable for agriculture, if not for drinking, is a really important thing. But then my final thing I want to go back to is a different one, which is the real importance of effect molecules, both as drugs and in controlling pests and diseases in agriculture. I can't see any way that we can do without them. And one of the disappointments of my career in chemistry is that we've made very limited progress, it seems to me, in being able to design new effectors. We know a lot more about the targets we'd like for drugs and to control agricultural pests, but it's really still quite a random process or a screening process to find completely new molecules. And surely that would be a fantastic challenge. If only you could take a target you want to affect and you could design yourself a ligand that did it. This would be just tremendous, because we're going to have forever, I think, competition with bacteria and fungi, that if they don't want to eat us, they want to eat the things that we want to eat out in the field. So I think it's actually a